Welcome again to the Illumination Talks, and today we're going to talk about ice ages, because this is a mystery that is still waiting to be solved. And since this will be quite a long and involved talk, I think it would be best to make this a two-part talk. So this is part one of the Ice Age mystery. And you might ask, what does Ralph know about paleoclimate? Well, as it happens, I wrote a peer-reviewed science paper on the modulation of ice ages back in 2016. And over 20,000 people have downloaded the paper and read it. So it's become quite an influential paper in climatic and paleoclimatic circles. So what is this mystery? Well, did you know that here in the 21st century, we still don't know why interglacials occur? And that's strange, isn't it? Because the science is supposed to be settled within climate. And yet within paleoclimate, we still don't know why ice ages occur. And in some senses, it's doubly strange because the impression is often given that scientists do know why interglacials occur, the ice age cycle happens. But they don't. So we're being given the wrong impression, and there is a big hole in the science there somewhere that needs to be filled. We do know, of course, that the ice age cycle is something to do with orbital cycles. And the particular orbital cycle we're going to look at is called the Milankovitch cycle, which was named after Milutin Milankovic, who was a Serbian, I think he was, scientist back in the 1920s. And this it calculated the insolation strength at 65 degrees north in the northern hemisphere. And by insolation, we're meaning the sun strength, the strength of the sunlight as it hits the ground, as I say, measured at 65 degrees north, because we think that is influential in ice age modulation. So how does this Milankovitch cycle change the strength of the insolation? What is the Milankovitch cycle? Well, it's combined really of three orbital motions, and we won't go through this in great detail, but it's nice to have some background information as to what is causing these changes in the sun strength, the insolation, during the centuries and the millennia. And the three cycles that combine to give us Milankovitch insolation are obliquity, and here is obliquity. So obliquity is the angle of the axis of the Earth. And as you can see here in this graphic, we've got the Earth leaning, as it does, about 23 degrees from the, as it were, the upright, in comparison to the orbital motion of the Earth. And it is this angle of the Earth, the angle of obliquity, that gives us summers and winters. You can see on this graphic that sometimes the northern hemisphere is leaning towards the sun. That'll be a summer. And sometimes it's leaning away from the sun. That's a winter. But this is on an annual basis. But in addition to this, obliquity also changes by up to 2.5 degrees over a cycle of 40,000 years, and that's the obliquity cycle. It's a 40,000 year cycle, and the axis of the Earth changes by up to 2.5 degrees. And that might not sound a lot, but it does change quite significantly the amount of insolation, the amount of sunlight that the Earth receives in the higher latitudes. So that's the first orbital motion. The second orbital motion is eccentricity. And as you can see from this graphic, the orbit of the Earth is elliptical. But it changes from elliptical to almost circular with a cycle of about 100,000 years. And so it oscillates between circular and elliptical and back again. And that doesn't actually change the insolation of the sun impacting the Earth at all. But it does change the strength of precession. And so we're going to look at precession next. So this is precession. This is just the general, we've seen this graphic before, I think. This is just the precession of a gyroscope. And you can see it precessing on its axis, it's wobbling on its axis. And the Earth does exactly the same. So if we look at the Earth precessing, you'll see this graphic will eventually change and it'll show the Earth wobbling on its axis. And that is precession. And when you combine precession with eccentricity, again you can change the amount of insolation that is impacting the high latitudes in the northern hemisphere, which is what we think is important, and we'll look at why that is important in a minute. So between all three of these orbital motions, you can change the amount of insolation in the northern hemisphere at 65 degrees north. And if we combine all three and put them on a graph, we end up with something like this. So here is a graph comparing insolation and temperature. So the blue plot is insolation, and as you can see, it's got a cycle, it goes up and down over about 22,000 years roughly is the insolation cycle. This is Milankovitch insolation, and every peak on that blue plot there is a great summer. That's when it's warmer in the northern hemisphere. It's a Milankovitch maximum, they normally call it. I call it a great summer because that's more illustrative of what actually happens, because when we're having a great summer in the northern hemisphere, the southern hemisphere is having a great winter. It's cooler. And then vice versa, obviously. When they're having a great summer down south, then we have a great winter up in the north. And this cycles over 22,000 years, roughly. It does change. So we get 10,000 years of the full summer cycle, and then we go into 10,000 years of the winter cycle. And that has an effect on the climate, of course, because the amount of insolation hitting the Earth in the northern hemisphere changes quite considerably. We're talking something like 20% change in the northern hemisphere, quite a lot. And therefore temperature will change. And you can see on here the red plot is the temperature change. And the temperature changes quite a lot. It's got a range here of 12 degrees centigrade. As measured in the poles, this is not the tropics, this is as measured in the poles. A change of 12 degrees between the interglacial and the full ice age. And, well, perhaps you can even see yourselves from this graph here. This gives us a problem, a big problem, a problem that's not highlighted enough, and it should be highlighted much, much more than it is. Because here we're looking at a graph of 450,000 years. So from left to right, we're looking at 450,000 years of climatic temperatures on the Earth. And these temperatures are taken from ice cores that are taken in Antarctica. And they give us a representative picture of the temperature changes over the millennia. And as I say, this graph gives us a problem because we can see the ice ages. So we start with warming, one of the red peaks. We start with warming and we get colder and colder and colder for about 100,000 years roughly. And suddenly we get warmer again. And each of those warm peaks coincides with a great summer, high insolation in the northern hemisphere. And you can see the red peaks and the blue peaks coincide. So interglacial warming is something to do with great summers, Milankovitch insolation, caused by the orbit of the Earth. But, and here's the but, many of those blue peaks do not give warming. Several of those blue peaks, if you look at them, give no warming whatsoever. So the Milankovitch cycle, the orbital cycle, is not the full answer to the Ice Age problem, because we are missing several cycles. And why would a cycle be selective? Why would a climate system be selective? Choosing some cycles and rejecting others. That's odd. And if we have an oddity like this, then the theory is not complete. And so the theory of Ice Age modulation is not complete. Despite what you may have thought and what you might have been told, the theory for ice ages is not complete. What we need is a feedback system, something on the Earth that can enhance the orbital cycle and give us interglacials, and therefore give us the full Ice Age cycle. And we can perhaps see this feedback system here, because this is the one we're always given. This is a graph of Ice Age temperatures in red versus CO2 in blue. And this is even longer. This is over 800,000 years from left to right. And we can see that as temperatures rise, so CO2 rises. CO2 is very, very closely correlated with temperature. And as we've been told on many occasions, CO2 is forcing temperature. So it's helping the orbital cycle to warm the Earth. And CO2 is causing temperature rises. You can see it. They travel together. Well, that's too simplistic. Much too simplistic. And again, we're being taken for fools, really, by the scientific community. Because there is a fundamental tenet of science that correlation is not necessarily causation. Just because one system follows another system doesn't mean that one is controlling the other. I mean, for instance, recent temperature rises correlate very well with American and Western Hemisphere milk production. But that doesn't mean that milk causes global warming. Correlation is not causation. We need to look deeper at this. And in reality, it is the temperature that's causing the CO2 to change. Because as the temperature warms in a warming world, and the oceans warm, the oceans are unable to hold as much CO2. They have less solubility, and therefore the gases are outgassed, and you get an increase of CO2 in the atmosphere. Now, scientists have said, that lack of solubility is not enough to show the amount of CO2 increase that we get during an interglacial, but nevertheless, it's a fundamental fact that as temperatures rise, CO2 will rise because of the temperature. So the CO2 rise is consequential. It's not causal. It's the temperature rise causing the CO2 rise, not the vice versa. It's not CO2 causing the temperature rise. And there are three basic reasons why we know that CO2 is not driving temperatures. The first of these comes from that graph again. So here's that graph. And if you look at it critically, you will see that when CO2 reaches a maximum, temperatures fall. So when we get to the maximum feedback of CO2, the maximum warming potential of CO2, the world cools. And you can see that here on this graph. And when CO2 reaches an absolute minimum, when there is minimum feedback and minimum warming from CO2, the world suddenly warms. But that's totally counterintuitive from what we've been told. CO2 should cause warming. So more CO2 should cause more warming, not cause cooling. And vice versa, in fact. When CO2 is at a minimum, we shouldn't get sudden warming, but we do. So that is a fundamental problem with the theory, with the classical theory of interglacial warming, of CO2 control of the climate. A second problem with the CO2 theory is that the CO2 feedback is very weak. Now, scientists will say that we get about 4 watts per square metre over the interglacial warming period, which lasts for about 5,000 years. That's about a 1% change. And that's relatively strong, you might say. And that will cause extra warming on top of the orbital cycle, the additional energy we get from the orbital cycles. But that's not how warming works. Warming works year by year, decade by decade, century by century. You have to get from one decade with extra warming, extra feedback, to get to the next decade. So you can't say that 4 watts per square metre is the amount of warming you get. What we want to know is in this decade, at the beginning of the interglacial warming period, in this decade, how much extra warming do I get in this decade to then force us to warm into the next decade? And the answer is we get about 0.006 watts per square metre. And that's less energy than a bee in flight. It's not much energy at all. And to be honest, that amount of warming is not going to force us into an interglacial. The third reason why CO2 is not the primary feedback for interglacial warming is that interglacials only happen when insolation rises in the northern hemisphere. So when we have a great summer in the northern hemisphere. They never happen when we have a great summer in the southern hemisphere. And you can see that on this graph that we've looked at before. So the peaks in the blue plot are the warming, the great summers, the warming in the northern hemisphere. And all of the interglacials happen with northern hemisphere warming. They never happen with southern hemisphere warming. But CO2 is a global feedback agent. And so interglacials should happen during northern hemisphere warming or southern hemisphere warming. They should occur equally. But they don't. They only happen in the north, and we'll see why in a minute. So with all of these three reasons, we know that CO2 cannot be the feedback agent controlling ice age temperature. And this is fundamental because these three logical deductions about paleoclimate undermine all of paleoclimatic theory. Every paper, pretty much, on paleoclimate is wrong. So why is this not mentioned by anyone? Why has nobody investigated other possibilities for interglacial modulation? I think it's because people are so wedded to the CO2 theory that nobody has researched or noticed anything outside their very narrow view of climate. Mentioning CO2 gives you a grant. Not mentioning CO2 gives you rejection or even dismissal. And so people don't look outside this CO2 box. And you might say I'm exaggerating here. This is not how science works. You know, science can look at anything. You know, that's the nature of science. But it's not. It's not the nature of science. Not the nature of modern science, that's for sure. I mean, look at David Bellamy. For those of you that are not in the UK, David Bellamy was the UK's favourite botanist and naturalist, a well-known scientist who is on television all the time. And he was loved by all. But in 2004, David Bellamy said that man-made global warming was poppycock. And he disappeared, just like that. He was dismissed. He was gone. Nobody knew what had happened to him. And later, I think it was in 2008, David Bellamy gave an interview, and he said about his disappearance in 2004, he said, "From that moment, I wasn't welcome at the BBC. They froze me out because I didn't believe in global warming. My career dried up. I was thrown out of my own conservation groups and I got spat at in London. And the worst thing, I got a letter that said David Bellamy is a paedophile because he doesn't believe in global warming and he's killing our children." How can science thrive in such a corrosive environment as this? I mean, the theory of man-made global warming may or may not be true. I'm a bit of a doubter on this one. I'm a heretic. But it may or may not be true to a certain degree. But this is not the way to find out if it is or not. This is the science of the Spanish Inquisition. Say what we say and think what we tell you to think. Because otherwise you will get dismissed. You will lose your career. You will lose your house, your family. Your career will be over. That's not the way to do science in the modern world. But that is increasingly what is happening. So let's do some real science. Let's put our thinking caps on and explore all of the possibilities, even the heretical ones. So what do we know about interglacial modulation? Well, the first thing is we know that CO2 is not the major feedback. We've already looked at that and we've, I think, demonstrated quite well that CO2 is not the major feedback agent that is helping the Milankovitch cycle. The other thing we've found out is that it tends to happen in the northern hemisphere. So the interglacials are what you might call hemispherically asymmetric. They prefer the northern hemisphere for some reason, the warming, the great summers in the northern hemisphere. And also, they need a very strong feedback agent, much stronger than CO2 can give. The CO2 feedback, when measured decade by decade, is simply not strong enough to assist an interglacial into a full warming period. So, what is the answer to this? What is the major difference between the northern hemisphere and the southern hemisphere that could cause this asymmetry in the warming response? Well, the clue here is that all of the major continents of the world lie in the northern hemisphere. So the northern hemisphere is full of continents, is full of land. The southern hemisphere is full of oceans. It's full of sea. And that can have a major effect, a climatic effect, a difference between the warming effects in the northern and southern hemispheres. And remember that if the continents are in the northern hemisphere, and therefore the Ice Age ice sheets are also in the northern hemisphere, there are no major Ice Age ice sheets in the southern hemisphere. And that again is a big difference. So how can ice sheets in the northern hemisphere cause temperature changes? act as a feedback agent to the orbital cycles? And the answer, well, if you think about it, obviously, big ice sheets in the northern hemisphere, and those ice sheets tilted towards the Earth because of precession and obliquity. The answer is albedo, the reflectivity of the ice. The ice is bright white, and it can reflect an awful lot of the inbound insolation that's going to hit the Earth. As much as 95% of the incident sunlight can be reflected back out into space again. And that reflected light, of course, is not causing any warming on the Earth. So the net effect is that all of this sunlight being reflected away causes cooling and causes ice ages. Okay, so what happens here? Well, the cycle goes like something like this. You get the world cooling for 100,000 years. That's a full ice age. And the world at that point is heading towards a snowball Earth. The ice age is getting deeper and deeper and deeper. There's getting more and more ice in the northern hemisphere, more and more reflectivity of that bright white ice, more and more albedo. And we're heading towards a snowball Earth. So how do we stop this process? How do we stop the world heading towards a complete snowball where the whole of the world ice is over? Well, what we must do is darken that ice, reduce its albedo. We've got to make the ice dirty. And you might say, well, you know, I'm stretching credulity here, making this up as I go along, because how on earth can we make all of the ice across the whole of the northern hemisphere? How can we make it all dirty? Well, the answer is we cover it with dust. And surprisingly enough, you might not believe this, but this is exactly what happens. So, and again, we have this information from the ice cores that have been taken from Antarctica, and they have a complete record of the temperature and the dust content of the atmosphere throughout the millennia for the last 800,000 years. And this is the answer. So here we have a graph of temperatures on the top in red and dust on the bottom in green. And you'll see, again, this is looking at 800,000 years of ice ages. And before every rise in temperature, there is a great deal of dust. You can see the dust peaks there in the green. So we do get huge amounts of dust before every interglacial. And this causes the ice sheets to be darkened, and therefore their albedo is reduced, and therefore they can absorb more sunlight. And this albedo feedback, as it's known, is very, very strong. CO2, as we saw, was only giving 0.006 watts per square meter. Albedo can give us 180 watts per square meter when measured regionally. And some scientists will say, because they've said this to me personally, no, you're doing this all wrong. You've got to calculate these figures globally because it's global warming. And my answer is not at all. For instance, what melts the winter snows in Canada? Is it the insolation, the incident sunlight during a Canadian summer? Or is it the temperature in Argentina? I would contend that what melts the snows in Canada, the winter snows in Canada, is the sunshine in the spring and the summer in Canada itself. Nothing to do with the global temperature. It's regional warming that causes the northern ice sheets to melt in an annual summer, and it's regional warming that will cause the ice sheets to melt during an interglacial as well. And that's why interglacials are a northern hemisphere phenomena. So now we have a full theory of ice ages. As we've just seen, the ice age cycle goes a bit like this. So the world naturally tends towards an ice age. We get snow in the northern hemisphere, high albedo, lots of reflectivity from this bright white snow, and that causes cooling. And we get more and more cooling, which gives us more and more snow, more and more reflectivity, and the world cools. And you're heading on towards the old snowball Earth. And this lasts for 100,000 years. That's the average age of an ice age, is about 100,000 years. And then we get dust on the ice sheets, which lowers that albedo, plus the insolation rise from a new great summer. So we get a lot of more Milankovitch insolation, as it's known, a great summer. And these together gives us a lot of warming, and the ice sheets melt within 5,000 years, a very, very short amount of time, and we get an interglacial. And that is an ice age cycle. And that just repeats itself time and time again. And this is what modulates ice ages. QED, you might say. Quod erat demonstrandum. We've demonstrated our theory. Well, not quite, perhaps. Remember that correlation is not causation. Just because the dust is correlated with temperature does not necessarily mean that it's causal to the temperature rises. What we need to do in order to turn this into a proper theory, a conclusive theory, is we need to prove that the dust increase is causal to warming, that it is dust that is causing the feedback, and it's not simply coincidental. And we'll do that in part 2 of this talk and demonstrate that dust and albedo are indeed controlling the ice age cycle.